Das, the floor is yours. Welcome.
Thank you. Thank you. Hello, everybody. So today I'm going to talk to you about a project that we started a couple of months ago, which focuses on using deep learning to address topics in software design. Now, this is a huge topic. We've done a lot of work, so I'm going to keep it as brief as possible. Let's see what we manage. But we'll first start with the question of why we're doing this. Let me see. Yeah, why we're doing this. Now, like Miroslav says, I work in at Volvo in the automotive industry. And at least one thing that many of us recognize and see happening is that there's a certain software intensification trend that's happening in the industry, right? There's a lot of features that are mainly software driven and that is being offered. And our hope is that this trend grows, that this software intensification trend grows. And once this happens, there's also going to be a parallel trend that grows, right? That is that a larger proportion of our R&D engineers are going to be writing code. And when that happens, there's a certain democratization of design questions that happens. I mean, you're going to have individual developers or individual teams wondering whether the design choices that they're making are sound. You're also going to have developers wondering whether the design choices that they've made translates across domain boundaries, across interfaces that they have set. And you're also going to have the ever-present architect community wondering whether grander ideas of architecture and design are being consistently maintained across repositories, across the overall system. So all these questions are going to pop up. And these are all questions from different perspectives. These are all questions that require different nuances. And these are all questions that requires a lot of time for people to address, which is why we sort of ask the question, can we use AI, or more specifically deep learning, to address these different perspectives of design and hopefully bring in some sort of automation on design questions. Now, whenever such a poser is placed, it's quite obvious, or it's quite fair that the alternative perspective comes up. Why use AI and not something traditional? It's not like design or architecture, the study of design and architecture in software engineering. None of that is new. I mean, a lot of this has been done for many years, but at least one thing that I at least have in my head is that in a lot of the classical approaches, if you want to put it like that, a lot of it depends upon precise definitions of design. Now, the very idea of software design is very difficult to define precisely, which means that checking it or enforcing it becomes a bigger problem. And you also don't want to do that very strictly because you don't want to cramp a developer's style, right? I mean, flexibility in design is something that is quite important for coders to be able to express their ideas, and you don't want to be restricting that. Which is why maybe an AI or a deep learning approach is more apt here, because this is not going to be a question about true or false. In deep learning is a world of likelihoods, it's a world of distances, it's a world of similarities. So it's a softer world, and hopefully a more nuanced world and a more complex world, and it provides the right kind of toolkits and the right kind of metrics that allows us to be able to answer questions about design. So that's essentially why we take a deep learning or an AI approach to this. Now, the use of deep learning in software engineering has been, I mean, it's been around for a few years. Now, a few years ago, people realized that expressing ideas in the form of a programming language is not all that different from expressing ideas in a natural language like English or Swedish. And with this explosion of the use of deep learning for natural language processing tasks, what people realized was that we could use the exact same pipeline and apply it for programming language understanding. So that's essentially the starting point of the use of deep learning for software engineering. And there have been a lot of cases where people have demonstrated applications like code completion, like code reviews, comments generation, stuff like that. So a lot of like routine tasks of development, people have used a deep learning approach to automate that. So that was our starting point. That's where we got on the train. So understanding that you can use a deep learning approach to coding, to understanding coding and programming language. That was a starting point. And then we will see, and I'll talk to you about how we sort of shifted that perspective into design. Any deep learning story begins with data. And in the case of programming language understanding, that is training expert programmers, expert machine programmers, the starting point is code. And you would be aware that there's large amounts of open source code available, and one such repository is the GitHub public data set that is that GitHub makes public via a Google Cloud BigQuery table, and there's a lot of open source code available there. So from there we picked up code being written in multiple languages. You can see the stats here, but the languages that we focused on were Java, Python, C++, and C. Why did we pick so many languages? Because we started by training models that were proficient in different languages. The first model that we trained was a language that's proficient in C. Now this is a bit of a no-brainer because a lot of the code that we write is embedded C, is an AutoSAR. So since that's the flavor with which we write a lot of onboard applications. So having an expert programmer in C helps us ask questions about design in C. But then what we also did was we trained a model that is an expert in Java programming. Now, why did we do that? One interesting thing is that when it comes to the idea or when it comes to asking questions about design, there's a very strong tradition of design and in the object-oriented community and specifically the Java community. So they have a bit of a head start in terms of doing design-based programming. So we thought that would be a good counter to have, so that we're able to consistently show our ideas both in the world of C programming and in a very design-oriented world like Java programming. Then obviously there's a lot of Java code also coming into the automotive domain, which is also why we train a cross-lingual model also. And XLM, that is a model that's proficient in programming in Java, C++, and Python. Now, we may not see a lot of Python coding in the automotive domain, but what is quite clear is that a lot of coding in the automotive domain is also becoming very multilingual. And another sort of germ of an idea that we had in our head is that a coder that is, that's proficient in more languages is more likely to be proficient in ideas of design also. So that's the analogy that we used to train these three different models: one that is proficient in C, one that is proficient in Java, and one that is sort of a master of three different languages. How did we train them? Right? You saw the data. These are the models that we trained. What was the objective? The training objective that we used to train these models. Now we picked up this very powerful, this workhorse model called mass language modeling, workhorse objective called mass language modeling that was introduced by BERT. This breakthrough NLP model that came out about 3 or 4 years ago. And the idea of training a model on programming is very simple if you use MLM. So the idea is essentially that, so let's say if this is the model that needs to be trained, you present it with snippets of code, but what you do is you blank out a few of these tokens. And the task that this model needs to do is to predict what should come in these master positions. And of course, from the corpus what the ground truth values of these positions are. And if the difference is backpropagated, and you do this for millions of hundreds of millions of files, then you see that the model has learned a quite sophisticated understanding, or a quite sophisticated. It has learned to predict this by seeing hundreds of millions of examples. That's much more than any human can go through. So in that sense, the model has been trained to become an expert programmer. And we obviously also make sure that it is an expert programmer by holding out a validation set and checking whether it does well, whether it generalizes well on data that it hasn't seen before. So okay, so we have now trained an expert in different kinds of programming. We've trained multiple experts in different kinds of programming. Now the question is obviously that, okay, so you are an expert in programming. Are you an expert in design? So that's pretty much the foundational question that we're asking. Now, these models have been trained on source code, right? And a source code is obviously a fascinating piece of information. If you look at if you look at a source file, then you could say that the core logical element is pretty much the backbone, or just the skeleton of the file, right? So the core logical flow of inputs, process, and outputs, that forms only a part of what's present in this. There's so much more information that's present in a source module, and one particular piece of that of all that information is design. Now, how does the world of design look? The world of design is quite messy, right? I mean, at the most basic level, if you attempted to sort of structure this universe of design, you would start by seeing that at the most basic level, there are very casual elements of design. One example that I always use is that, I mean, for example, if you looked at how people wrote unit test cases, you would see that there's remarkable consistency in how people approach writing unit test cases. There's also remarkable consistency in how people write, log statements or audit logs or something like that. So there's a lot of design that goes into code without you being specifically taught to do it. So there's a lot of casual design that happens in coding. And then you also have convention-based design, right? Autisar is a fantastic example. So if you look at the Autisar software component, the idea of read ports, write ports, run, so that the idea of partitioning logic like that is enforced by a certain convention. And if you're in the machine learning space like me, you would also see that the design of a training loop is also very consistent. So these are also ideas of design that's both common sense and enforced by convention. But then you also have a much more structured approach to design, like design patterns or something like that. So there's like this whole universe of design is very messy, is very big. But one thing that we can say is that having trained our programming language understanding models on hundreds of millions of source modules, now there is a quite high likelihood that it has seen all these different kinds of design. So that's why the first set of experiments that we do is to just check, is to evaluate the expert machine programmers to see if they have understood ideas of design. Now, there are many ways to do this. I will show you at least one way in which we approach this thing. So I mentioned before that what you do with this model is to show it snippets of code, that is, words or tokens of code written, and the model processes it. So let's look at the very idea of source code tokens and how design comes into that space. It's very let's look at the vocabulary of words that we use in expressing programs, right? If you looked at our corpus of 200 million files, you're obviously going to see a huge set of words that are expressing a vastly different sets of ideas. But if you looked at a very specific subset or a specific corpus that focuses on a certain thing, like, for example, Autisar, right? If you looked at the whole, the big vocabulary of that you use to express ideas in programming, and you looked at the vocabulary that you use to express Autisar, now you will see that there are very identifiable recurring elements, like, for example, RTEs or ports or signals. You will see those words being expressed more in a corpus that is, that's specializing in expressing ideas with an Autisar design. And you would also see something very similar if you look at a Java design patterns corpus, and I mean a corpus that follows design patterns very religiously. So you will see instances of singletons, factories, decorators, blah blah blah. You're going to see this thing. So one hypothesis that we have is that when you come up with a new idea of design, or when you come up with an exclusive idea of design, what you typically do is you specialize the vocabulary space. Now, if you think about it, it's quite intuitive, because the idea of coming up with a new design is usually associated with coming up with a new phraseology, a new terminology, a new lingo. So that's typically how you. There are other things that you do too. There are many structural elements. There may also be behavioral elements, but purely in the token space, but purely in the vocabulary space, you will also see traces of software design. Now, this sort of a construction is very helpful for us because it lets us evaluate the model with a similar masked language modeling trick that we use. So this specialization in the token space is basically the foundation of the experiments that we do. And in our very first set of experiments, what we did was we picked up an open source data set called PMART. I didn't mention this. I should probably add that. So we picked up a data set that focuses on Java design patterns. Now, this is a data set that does focus on Java design patterns, but that's not all it does. It does other things too. It actually implements a lot of logic and a lot of flows. So this is a complete set. It does a lot of stuff, but it also follows specific design ideas. So what we did was, in this particular combination, so we took its vocabulary, and then we saw, and then we checked whether the model is relatively weaker in handling these design keywords in relation to these keywords that that are purely syntactic or purely logical. So this is pretty much the idea that we built upon, and we did this test. Now I will present some very basic results. We'll maybe come back when we have when we've done a better analysis. So what we did was we checked we took the same recipe. That is, we blanked out certain tokens, and then we saw how the model was the ease with which the model is able to predict these blanked out tokens. And to help us do this analysis, we used a very standard explainable standard technique that is used in machine learning explainability called Shapley value analysis. But that's not important. But what we essentially found was that if the model is tasked on predicting, very syntactic elements like a binary operator or a semicolon or a parenthesis or something like that, the model is very good. The model is very good in doing that. And the same applies even to a lot of syntactic elements in code, like syntactic keywords like int or for or while or something like that. But if the model was being asked to predict, if we blank out a keyword that has a major design that's of major design significance, and we ask the model to predict that word, which means that to predict it correctly, it would have been it should have had a fairly good understanding of what this design is. We found that the model was doing slightly worse. Now you have to understand that the model doesn't totally collapse. It's not like the model does goes to zero. The predictions go down to zero. The average prediction accuracies are still quite high, but you can see that there is, the model slightly does slightly worse on predicting these keywords that are of that hold complex design ideas. So this is just a first indication of maybe the fact that there is a slight there are signs of relative weakness. That is, the model is able to understand syntactic elements much more than design elements. Now, there are many. We have many explanations on why this is happening, and we also have much more detailed analysis of what's happening here. But Miroslav says 20 minutes, and I don't want to go beyond this. Maybe we can do it later, but this is pretty much what I had. So I hope that you've gotten an idea of why we're using deep learning to approach design, the benefits that we can gain from it, and one aspect of how we are testing an expert programmer in design, that is to use the idea of specialization in the vocabulary space and see if the model is relatively weak or strong. First, but please remember the verdict. I mean, we don't have a strong verdict yet. We're still in the process of investigating. This is just a first sign. So please don't think that the model is a bad designer yet. We don't know that answer. So, but that's all I have. We have plans to continue working with this, but I think it's best to stop here and open up for questions.
Thank you very much, Das. Let me stop the recording and then we open up for question.
All right.